Hello and welcome to my video, lesson 4.2 on the speed of light. So obviously speed of light is something extremely hard to measure because it's so darn fast. People used to think that it was instantaneous, infinitely fast, according to Descartes. But by accident, this guy discovered that light actually has a finite speed. He didn't get a super precise answer for it, but in 1675, humans discovered that there is a speed of light. And after that, we've just been getting better and better at measuring it. So basically what he found is that the Earth is here, E, and Jupiter is up here. Whoops, my eraser. Jupiter is up here, J. And what he was looking for is the period of the orbit of the eclipse, or the eclipse of Io, which is a moon of Jupiter. So basically, how long does this moon stay behind Jupiter? How long does it take for it to get eclipsed? And what he found is that when the Earth was moving, like in this position, moving away from Jupiter, okay, and actually this diagram is not super good because it's actually going to be more like this. When it was moving away, they found that the eclipse seemed longer. Okay, on the other hand, over here, when it was moving towards Jupiter, they found that the eclipse was shorter because the Earth was catching up to the light, sort of thing. So it's kind of a weird one, but that's what they found. So there's those two different situations, and they realized that there was a difference between the two periods, and that's why they figured out that there is a speed of light. So over the years, we did different experiments to try to measure this better. We're going to focus on two of them. First of all, the Michelson-Morley experiment in 1887. This is the first really good measurement for the speed of light. Yeah, there were others, but this is like a fairly good one. It's pretty clever because it uses rotating mirrors in a setup kind of like what's here. Okay, and this mirror setup, this 8-sided mirror, will rotate around in a circle, and at certain angles, it will shoot the light to the other stationary mirror on a different mountain, and then it'll bounce back, and the mirror will have spun in that time that it takes for the light to travel from here to here and back. That's the time it takes. So this is however much time it takes, okay? From going from there to there and back. Okay, so V equals D over T. Okay? Now, that's what they found for that portion of it. And at the same time, they're spinning the mirror. If the mirror was just stationary, I mean, you wouldn't know your time. So this is the question. What is the time? We know the distance. It's 35 kilometers. And we'll actually do the calculation down below with the proper values for this experiment. But we know the distance. We can measure that. The question is, what is the time? Well, how do they figure out the time? They rotate this mirror around. And if it is not rotating at the exact right frequency for this to have a mirror at this angle, then it will not work. But if it rotates at the exact right frequency, then it will have this angle, and that's when the light travels to the observer here, or usually a measuring device. So you need to have this mirror rotating at a specific frequency, okay? And every 1/8 of a turn, okay, whatever frequency that is, if you times that frequency by 1/8, every eighth of the turn, or actually the period, I should say, every eighth of a turn, that would be the time that it is over here. So you can figure out the frequency, which is going to give you your period, because period equals 1 over frequency. Then you multiply that by 8, or 1/8, sorry, and then you put it down below. Okay, so let's go down here and take a look at another experiment. So again, this is kind of the, actually I'll show this one with the three-dimensional thing. It shoots the photon here, it bounces off and comes back, and by that point this has rotated by 1 and it will go in here. If it doesn't rotate fast enough, then it's going to get bounced off this way. If it's too slow, okay, or if it's too fast, it'll bounce off this way, too fast, depending on how fast the mirror is rotating. Okay, pretty cool experiment, but they were able to come up with another experiment in 1848-49. Actually, that would be, interesting. We've got two different times here, two different dates for Michelson and Morley. But they were all kind of figuring it out all at the same time and verifying each other's data. But this one looks like it maybe came first. So this one is an experiment by, I'm going to say Fizeau. I'm not sure how to pronounce the name. But basically, he had the same idea, but he shot the light through a, let's say, one-way mirror or a piece of glass, and then through a set of cogs here. And these cogs would have holes every once in a while that would let the light through, and every once in a while the teeth would block the light. Okay? And so these notches or cogs would be the two different options, either letting light pass or not. Then the light would go through from here to here and back. So again, this is your V equals D over T. If you just measure that D, which has to be a very big distance, many kilometers, then you can figure out the rotation of the cogs, and then you can multiply and figure out like the hertz of the cogs, and then you can get the time, and then you can get the speed of light from there, because it will continue to pass through and up into the observer. So here are two different questions based off of those two experiments. I recommend you pause the video now, try it yourself, and see if you get the same answer as I do. Okay, so these are the numbers that I was able to Google about their experiments, so we'll see how accurate their experiments were. Basically, Fizeau guy set up a mirror on a hill this far away. Okay, which means that we do know the V equals D over T. We know the D. Okay, the D is 8,633 meters. Okay, but maybe first of all, maybe he wasn't able to measure a straight line like that in the air quite so perfectly, but he measured it as best he could. The other thing that he had was that he was looking for the hertz. Okay, because if you knew the frequency of the cogs, then he could calculate the time and therefore the speed. So we're going to look for the time. Now the time is related to the period. Period is 1 over frequency. So 1 over frequency, well, we know that it's 1 over 12.6 hertz, which is 0.079365 seconds. Okay, and the light was eclipsed at that speed, and it was fully visible, i.e. it hits the next cog at 25.2 whatever 5 seconds. So the question is, which of these two numbers do we use? 0.03968 seconds. Okay, well, what does it say here? It has 720 notches. That's how many cutaways it has. So if you spin it by 1/720th of a turn, it will be at the next notch. It'll be at the next hole. So this number lines up with this period. So we want to not spin it all the way around, which is how far it would travel if you did this. But if you only spin it 1/20th, or 1/720th of that, so essentially take that number and divide it by 720. So multiply these two and you get the time, which is 0.000055115. And this is how much time it took to travel that distance. So now that he has the time, now he can go ahead and plug it back into this formula here, which is going to be 8,633 divided by that time that we figured out. So we get an answer of 1,566. I'm going to say like this. 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8 meters per second, which is in the right ballpark. Let's just see here. We've got 3 sig digs everywhere, so actually it should be here. 1.57 times 10 to the 8 meters per second. It's in the right ballpark. It's not perfect, but with it's on the same. It's in the same range. They're both times 10 to the 8. So it's pretty close. Oh, actually, I've forgotten something. The hill is that distance away, but we actually need to double that. Why? Because the light travels there and back again. So, times by 2. Oh, that's so much better. It should be 3.13. Oh, that's pretty good. Meters times 10 to the 8 meters per second. So that is the speed of light that Fizeau calculated. So not bad. Now, if it's saying what is the percent error in measurement, what you're going to do is you're going to find the difference between the theoretical and the experimental. And you're going to divide it by the theoretical. Now, we know the theoretical to be 3 times 10 to the 8 meters per second. So, considering that, and times 100%. That's up top. So that gives us an answer of 4.42% error. So not bad at all. I'm just going to adjust my calculation here so that it says times 10 or times 100% on the side. Okay, not bad at all considering what this person probably had to go through to get these results. Not bad at all. Okay, so the a much more recent result is in 1926. Alberta Michelson measured the speed of light using an 8-sided rotating mirror. So very similar, basically the same, maybe even the same experiment as this one. And he had the mountain 35.5 kilometers away and rotated the mirrors at a rate of 5.28 hertz. He found that this was when he would first see the light bounce off the mirror, because I just want to point out here, if we consider this previous question, then this is the first time it works. But the second time would happen at 2 over 720. The next time would happen at 3 over 720, etc., etc., etc. So that one is the first time. And so this is the same thing happening here. When is the first time that it would work? Well, that speed right there. And it's an 8-sided rotating mirror. So it's the same concept as before. Just keep in mind that your D should be 2 times 35.5 kilometers. And so what is the T value? Well, that's what we're gonna have to figure out. So the T is found from this experiment, or this concept here, 1 over frequency. That's the period, which is going to be 1 over 528. Okay, and then we're going to take our period and times by 1 over 8, because we're using an 8-sided mirror, so we're getting an 1/8 of a turn is what we're looking for. How long does it take to do an 1/8 of a turn? The answer that we get is 0.0002366742. And then we can plug that into the previous equation over here, which gets us 2.999 times 10 to the 8 meters per second. And considering that we have 3 sig digs everywhere, 3.00 times 10 to the 8 meters per second. Which means that this is actually, if you talk about percent error, this has 0% error, because it is exactly the same, theoretical and experimental. So that is a very good result for the speed of light. Alright, I hope this video helps you understand both of the different types of experiments, the cogs and the mirrors, and how we are able to figure out the speed of light as humans. Hope this video helps, and good luck.